Hi guys, and welcome to today's Autodesk Inventor Fusion CAM demonstration. So part of today's demonstration, we're going to take you through Inventor and Fusion CAM software. Now this software you get with your product design and manufacturing collection. It comes with Autodesk Inventor and it allows you to simplify the machining workflow with the CAD embedded 2.5 to 5 axis milling, turning and mill turn capabilities. Okay, so you've got your 2.5, your 3 axis, your 4, 5, you can turning and mill turn. You've got your water jet, plasma, laser cutting, probing, tool holder avoidance. There's many different features that come as part of the Inventor Fusion CAM package, along with other things you get with the product design and manufacturing collection, such as Inventor nesting and tolerance analysis, and other products such as Nastran. Nastran we'll cover in a different demonstration. So I will hand over to Francisco, who will take you through the demonstration.
Okay, welcome to today's webinar. Today we're going to be discussing Inventor CAM and Fusion CAM. So we're going to be seeing some of the capabilities of these softwares for producing machining tool parts, both with milling and turning. So before we get started, has anyone used CAM software in the past? Feel free to use the chat box in the corner. No, that's okay. We'll just dive right into it. Okay. So in Inventor CAM, it is possible to produce 3D machining tool paths for export onto machining programs. To see what that looks like, we'll come along here and we'll quickly have a look at this setup. We'll see the finished product before making it ourselves. And click here, simulate. And here we can see a 3D model that has been fitted with tool paths, instructions for a 3D cutting machine. It seems to be going a little bit choppy. But yes, okay, today we're going to be seeing how we can produce these tool parts within Autodesk Inventor and Autodesk Fusion 360. So we'll get started. To begin, we'll start with a 3D model. Our first 3D model is just going to deal with 3-axis machining, which will mean that the machine will be able to come in and perform X, Y, and Z cuts without doing simultaneous actions. So we'll begin by creating a new setup. Our setup allows us to define the stock as well as the orientation for the machining tools. So here we can choose the operation type milling. And for the orientation, we'll select Z-axis and X-axis. Because in modeling, Y is up and in machining, Z is up, we need to change the universal coordinate system. So here we go. We'll select that surface to be indicative of the Z-axis. And for the X-axis, we'll pick this edge here. For the stock point, we can select one of the corners. Next, we can come over to the stock tab, and here we can define the stock. This is the part from which the bit is cut. So here we can select a relative box size, and here we can specify offsets. We may put a 2mm offset on the sides and the top, and perhaps a 10mm offset on the bottom, something for the vise to hold on to. Next, we'll click OK. So the first operation that we'll want to use is a facing operation, in which case we'll get a big face mill and we'll cut it along the surface. We'll come over to the face tool. And here we have 5 tabs for defining the operation. tool, geometry, heights, passes, and linking. Starting with tool, we'll go ahead and we'll select a 50mm face mill. Next, we'll come over to the passes tab, which defines how the passes are, and we will say a stock offset pass extension of 13mm. When we click OK, we get a preview of the tool paths that will be used. If we click Simulate, we can see the toolpath in action. I will turn on stock and turn off toolpath. And when we hit play, we get a preview of how the tool interacts with the material. It seems that the recording is forcing the animation to be a bit slower than I'd like. But there we go. Once the simulation is complete, we can compare the cut part with the actual stock. Next, what we want to do is introduce a 2D adaptive toolpath. This will be used for roughing the area. So it's a rapid operation using a sharp tool for clearing out as much material in as short a time as possible. We'll start by clicking 2D adaptive. And we'll change our tool to something a little bit more sensible. We'll change it to this 6mm flat tool. That looks good. For the area to clear, we'll select this interior pocket as well as this one here. Coming to the passes tab, we can elect to have the cutter cutting both ways by ticking on both ways cutting. And then coming to the linking tab, here we can choose how long the tool stays down, how much it retracts by, what's its stay down level. Clicking OK, we will get a preview of the operation that gets created. Let's finish this calculator. There we go. So if we can read these toolpaths, we can see that the tool is lunging down and then turning into a spiral, and then commencing its roughing operation in both pockets. We can quickly see what that looks like here. Coming to setup and simulate. We can now hit play. Okay, now that we have the roughing operations out of the way, we can come with a 2D pocket. 2D pocket is similar, except that it's intended for finishing operations. So for this, again, we will select our two interior pockets. And for the passes tab, we will untick stock to leave. This will mean that it will leave no stock radially or axially, meaning that it's a finishing operation. We'll come here to OK. And as we can see, the tool is not staying down as intended, so we might change some of the parameters. Here, we can come to the passes tab and change the maximum step over from 5.7 to 3mm. Coming to the linking tab, you can just make sure that everything's okay. Yeah, wonderful. Okay, now as we can see, we begin with a facing operation to remove the top material, then proceed to an adaptive clearing operation to rough out as much material as possible. But when we come to the 2D pocket operation, we can see that the spirals are continuing from high up. We can change this behavior by editing the operation and changing the initial height of the operation by coming to the heights tab, and then changing the top height from stock top to selected contours, and then plus 1mm. This means that the operation will just start 1mm above the surfaces. Beautiful. And I think we can get it simulating quickly this time. That's it. Wonderful. So we've got our facing operation coming in here. We have adaptive clearing, which rapidly removes material using a tricordial operation. And then we have our finishing pass using a pocketing operation, which should leave a nice finish on there. And by turning on part comparison, we can see that the material in blue is a material yet to be cut. So as we can see, we've got 4 holes in the corner, 2 bore holes, and some chamfers to cut out. Easy. Next, we'll come along and we will add a boring operation. So we'll come here and select bore. Oh, here it is, bore. And keeping our 6mm flat selected, we will choose the 2 bore holes that we wish to cut out. Now, by default, it's just cutting to the bottom of the holes. We might want to change it so that it punches through the bottom by adding in an offset in the heights tab. There we have our boring operations. And next, we might want to do the drilling operations in these corners. So we'll come along here and select drill. And firstly, measure the holes, 4mm, select drill. Choose the tool. And here we'll choose by type, drill, and scroll down to 4mm. Of course, when using it in an industrial setting, you would have your own tools programmed into this library so that you know exactly what you're going to be using. In that operation, I selected all 4 of the holes, but that's not strictly necessary. I'll just unselect those. Select the first hole, and then select same diameter, which will select all the same diameter holes within the region. Now, as before, we can see that the drill tip is just touching to the bottom of the hole, but in reality, we'd probably want it drilling a little bit further on. So to do that, we'll come to the heights tab, and we'll say hole bottom, drill tip through bottom, then 1mm through the bottom. Lovely. In the final tab cycle, here we can see what type of operation is being performed with the drill. So here we can just choose drilling with rapid out, dwell and rapid out. Usually for tough materials, we use chip breaking partial retract, in which case the drill will go a little bit in and then a little bit out, a little bit in, a little bit out, a little bit in, a little bit out, and clear the hole as it goes. We're going to leave a little dwelling period at the end of 0.2 seconds and click OK. Excellent. And the last operation to include is a chamfering operation, in which case we'll get rid of the chamfer on the outside and on each of these features. So to do that, we'll come along to chamfer. 2D chamfer. And choosing, well, it's automatically selected the chamfering tool, but we'd select a 45-degree chamfering tool. And here we'll choose contours. So we'll pick that one there, this one here, this one here, oops, this one here, and this one here. And clicking OK. Oops, it is by chamfer pairs, by contour pairs. There we go. Clicking OK. We get the tool paths for the chamfering tool. So let's have a look at what that looks like. We'll come here and click Simulate. And we begin with a big facing tool that will remove the top material. A roughing operation with the 2D adaptive. Followed by pocketing operation for finishing. And I'll slow it down a little bit here. Now we've got the boring operations coming in which case the flat mill will come in spiral pattern and bore out those two holes. Next, we've got the drill coming in, taking out the drill holes. And finally, the chamfer tool coming into chamfer. Now, there is one operation that's missing here. We need a contouring operation to contour the outside of this part. So to do that, we'll come to 2D contour. Choose our contouring tool. In this case, we'll choose a 25mm flat. Why not? For the heights, we will choose a bottom offset of -1. And a finishing overlap of 4mm. And I'll position that above the chamfering operation. With the finishing overlap of 4mm, we can see that it repeats the path just a little bit so that there's not a cusp left over. And doing one final simulation, you should see the face, the roughing, the pocketing, boring, drilling, contouring, and finally the chamfering. And if we turn on one final part comparison, we should see that the part is as we intended it to be cut. Perfect. Okay, and click close. And that was the 2D milling operations. So what that involved was using 3-axis machine without doing simultaneous operations. We'll have a look at some more complicated things shortly. We'll save that and close down. And we'll open up the next. Here we'll come to 3-axis simultaneous. So this is, again, using a 3-axis machine, but this time it's going to be using more than one axis at the same time. So we'll come over here to environments, to CAM. And again, we'll create a setup from a stock. So we'll click setup. And as always in machining, Z is up. So we'll orient it so that the Z axis is facing upwards and X axis in this direction. And the stock box point is in this corner here. For the stock, we'll come along and we're going to say a relative box size, but we're going to leave 0 on the top and sides. For this, we're going to take advantage of some 3D milling operations. The first is going to be an adaptive clearing operation, which is going to use tricordial milling in 3 axes to clear out bulk material. We're then going to come with a scallop operation to nicely remove the material on this complicated geometry. So with the adaptive tool selected, we'll choose a tool. In this case, we'll come to a bullnose mill, perhaps 3mm. And we're going to leave it with its default settings. Well, stay down. And what it's doing is it's calculating a 3D toolpath for rapidly removing as much material as possible as quickly as possible. To see that in operation, we'll come along and set up and click simulate. Here we go. We can see that it's using approximately 80% of the flute length of the mill to systematically remove as much material as possible as quickly as possible. So this is a roughing operation intended to get rid of as much material as quickly as possible. It's not actually intended to leave a good material quality. Ooh, that plunging operation there was probably not the most efficient way that we could have done it, but that's okay. A little bit of tweaks and we can remove that. So once this roughing operation is done, we can see the approximate shape of the part that we want to cut out. To get a nice finish on this, we could take one of the other 3D milling operations and use it. So in this case, we're going to use a scallop material, a scallop tool. So here we'll come along and this time I'll choose a ball nose, as small as I can get it. Maybe not long enough. We'll choose the 3 mil. There we go. And what we're going to do is we are going to specify a step over. So this will be essentially our cut resolution for the part. So we'll say a step over of 0.5 millimeters. It looks okay, but I think we could do better. We'll edit the step over so that it's 0.2 millimeters. Lovely. And now we can see a machining tool part that conforms to the surface of the 3D part, cutting away the material it can. This, it's important to keep in mind that this is not a 5-axis simultaneous thing. The tool's angle is not changing. So here we'll click Setup. We'll click Run. And here we've got our adaptive clearing from before. And now our scallop operation. And if you give it enough time, it should remove a lot of material. Not seeing any collisions. Because we're using a ball nose cutter, cusps are unavoidable in this circumstance. And if we turn on part comparison, we can see how the part compares to its form. As we can see, there were little bits here and here that we couldn't quite reach with the 3 millimeter cutter, but I think it looks pretty good. Okay, clicking close there. We'll go ahead and we'll save that and close it down. Now, I mentioned earlier that we'll be demonstrating both Inventor and Fusion 360. The CAM environment between the two are very, very similar. So this is Fusion 360 with similar modeling tools, CAM tools, simulation tools to Inventor. What we're going to have a look at here is not only the Fusion 360 CAM environment, but also how we can do 3+2 axis machining. So what that means is doing 2D machining but on different planes. So to do that, we'll come to the Manufacture tab. And what we're going to do here is we are going to create a new setup. So as before, we're going to choose a milling setup. And for the orientation, we'll select the Z-axis and the X-axis. For the Z-axis, we'll have a face that faces upwards. And for the Z-axis, we'll choose any one of these lines going in the X direction. For the stock box point, we can put it in the corner here. Great. Now, for the stock, here we can choose a relative box size or a fixed box size or yada yada, but it's also possible to choose another solid body that exists within the 3D model. So I'm going to click Cancel here and come back to the Design tab and show you what I mean by that. If we expand our bodies, here we can see that we've got two separate bodies. One is going to be the stock from which we're going to cut, and the other is the object which we want to cut out. So at the moment, I have them both selected on, and so they're both overlapping each other, which is fine. We'll come to the Manufacture tab, and this time when we do our setup, we'll go ahead and we're going to choose, again, the model orientation that's before. Might need to flip the X-axis, there we go. And for the stock, we'll choose from solid. And selecting body to stock, you can choose that separate solid body as the stock from which we're going to cut. And I'm not sure if I choose a model. For the model, I'll pick object to be cut. Great. And for clarity, I'm going to turn off the visibility of the stock. Okay. Next, what we're going to do is a simple slot operation and 2 drilling operations on one of these faces. So to do a slotting operation, we'll come to 2D and we will pick slots. And before we do, it's always good practice to measure. We can see it's got a 12mm diameter. So we'll pick 2D slot and pick one of these slots. Now, as you can see, because the orientation of the part is Z is up, when we chose this slot, it's actually picking a profile in line with the Z axis we specified. However, with 3+2 machining, we want the axis to change with an operation. So here, under the geometry tab, we can pick tool orientation. And now what it allows us to do is change the tool orientation to choose another face. So we'll click this face here. And for the x-axis, this line here. For the stock box point, we can select here. Okay, so now we can click OK, and we can see this operation. We can see that our tool comes down, plunges, and then it zigzags in. And that looks good to me. Okay, next what we want to do is come along here and measure these holes, 8mm diameter, and choose a drilling operation. And in the same way, we'll come along here and we'll pick with the geometry, the hole faces we wish. Now, by default, you can only pick the holes in the direction of the universal Z axis. But because we want to pick it on the side, we can come to the geometry tab and click tool orientation and simply pick this face here and the x-axis. And to be pedantic, let's go ahead and choose the box point as well. There we go. And for the geometry, we'll pick these 2 hole faces. Lovely. For the cycle, we'll choose, as we did before, the chip breaking with a little bit of dwelling on there. Oops. With a little dwelling period on there. Dwell before retract. Lovely. So let's go ahead and hit the simulate button and see what that produces. So here we hit play. Oops. And we can see that it comes in and does, oh, this is the previous setup. Here we'll hit simulate. There it is. Hit play, and there we have our slotting and our drilling. I believe it is mistakenly using a drill for the slot, so I will correct the tool being used. Edit, select tool, and we'll choose a 12mm flat. That's better. Click simulate, and here we can come in and we can see the 12mm flat mill carving out a slot, then a drill. Great. Okay. So we want to repeat that operation without having to laboriously respecify each one of those operations. So to do this, what we're going to do is we are going to add each of these to a folder. So we'll create a new folder. And into that folder, place those 2 operations. And we're going to grab that folder and we are going to pattern it. So to do this, we'll come along to, where is it? Modify actions. Yep. One moment. Action. Ah, there it is, pattern. Lovely. Okay, and we can choose that folder. new pattern. And here we go, choosing the pattern type, a circular pattern with the axis specified as the y-axis of the model, which is the z-axis of the part. And here we can specify the number of instances. So we'll change it from 2 to 4. And we can see that the same operation is copied onto each one of those faces. So hitting simulation now, we can see that the slots are first cut out, and then the drilling operations are all done. A nice thing about that is that you can see that the slotting operations were all done before all the drilling operations are done. This minimizes the number of tool changes. So that was 3+2 machining. We'll go back to Inventor now, and we'll have a look at 5-axis simultaneous machining. So during the scallop, I mentioned that the tool's angle doesn't change. It just engages multiple axes at the same time. It is possible, however, to have a tool running along a surface. So we're going to have a look at that with this operation. So here what we've got is a part that has a curved surface to it. It's also got a chamfer that needs to be cut out using a swarf operation. So we'll have a look at how to do this. You can do the same in Fusion and in Inventor. Here we'll come along to the setup, and we'll choose a stock model orientation first. So Z-axis and X-axis. For the Z-axis, we'll pick the model's Y-axis. And for the X-axis, we'll pick the model's X-axis. For the stock box point, we'll pick this corner here. Next, we'll come along to stock and choose relative size box. And we'll add 2 millimeters to the top, 2 millimeters to the side, and about 10 millimeters to the bottom so that we can grip the thing. And click OK. Next, we'll come along with a 2D contour. So we'll come along 2D contour, and we'll select a large tool. We'll choose a 14 millimeter flat and pick this lower contour. Under the passes tab, it's possible to do a few roughing passes, which will execute radially. Choose 2 step overs, click OK. And here we can see how the operation begins. So we'll start off with a box. And it'll start wide. And start cutting in. Lovely. For good measure, it's always good to cut beyond the lower surface. We'll see, -1 there. Great. Okay, next, what we're going to do is an adaptive clearing operation. So as before, we're going to choose adaptive clearing. And this time, maybe we'll use something a little bit less aggressive. We'll choose perhaps a 6 millimeter bull nose. So the adaptive clearing operation is intended to just remove as much material as possible as quickly as possible. But it's not intended to be a finishing operation in the slightest. So don't be horrified by the toolpath it creates. Beautiful. Well, not beautiful, but functional. Here we go. Okay. Now, what you find when we do the adaptive clearing operation, if you keep an eye on the tool's orientation, it's always upright. That's the same whether you're using a scallop or a 2D contour or 3D contour. It doesn't really matter. It doesn't make a difference. However, as we can see, this surface is a flat curve. So it might be possible to actually cut this out if we have a 5-axis simultaneous machine. So to do this, we'll come along to the flow toolpath. Choose this upper surface here. And this time, we're going to yeah, we can keep the 6mm bullnose chosen. Under the passes tab, here we can choose use multi-axis. And what this allows us to do is change the angle of the tool. Now I'm going to start off with the potato number of stepovers. So we'll just say 8 stepovers just so that you can see it in operation. There we go. And I will simulate just this operation without the stock turned on. And you can see how the tool interacts with the surface. We can see that the tool runs normal to the surface at all times. Now, of course, if you want a better finish, we're going to need to use smaller stepovers. So we'll come over here, choose passes, and for the number of stepovers, we'll choose 40. That looks better. And lastly, we'll need to do a swarf. So we'll need to come in with a tool at an angle to cut out this steep chamfer all the way around. So to do that, we'll come along to swarf, pick our chamfer. I prefer by contour pairs. We'll go contour pairs. And for the tool offset, we'll choose -1 or -0.5. And for the tool itself, we'll come and choose a, let's see what we've got. We'll choose the 6mm, maybe a flat. There we go. We can click OK. And if we click the simulation tool, just with the swarf, we can see it might have some collisions without some modification. There we can see the swarfing tool come along the edge. So if we grab all of our operations and simulate it, hit play. We can see how our part will look like at the end. And by turning on part comparison, we can see in blue the bits that haven't been cut out. Perfect. Great. Okay, so that was 3-axis machining, 5-axis machining. There's one more thing that I'd like to show you for this demonstration, and that's the turning operations. So we'll save and close that down. And we'll come here to turning. So here we have a simple turned part. It's just going to involve a few operations, but basically what we've got here are 2 grooves. We've got the desire to face the machine, to drill it, and to do a smooth profile. So to do this, we'll come over to the CAM environment again, and we'll come to the setup. And here, for the operation type, we'll choose turning and/or mill turn. And here we can see a lot of the same operations as before, but these times specified radially. As before, we'll choose the Z-axis, looks good. For the stock, we'll choose a relative size cylinder. So here we can specify a cylinder that has maybe a 2mm radial offset, a front side offset of 2mm, and maybe a backside offset of 10 millimeters, so that we can grip it. We'll click OK. And next, what we're going to do is we're going to begin with a facing operation. So under the turning tab, here we can see turning face. And here we can specify what tool to use. So we'll use a general turning tool. There you go. A general turning tool. And it's a bit boring because it tends to do it perfectly the first time, the facing operation. We'll come here and we'll see what it looks like. Simulate. Turn off part comparison, hit play, and it will just face the front of the part. Okay. Next, we want to come along and do a rough profiling. So we'll click rough profiling. And here, what the Inventor will do is automatically pick up on the turned profile of the part. So we'll come to the passes tab, and we can specify whether it will radially or axially groove. By default, we're just going to say don't allow grooving. And click, we're going to specify a stock to leave of 0.1 millimeters and click OK. And here we can see our two operations. So we've got our facing operation coming in and then our roughing passes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nice. Okay, so this is just intended for roughing. If we turn on part comparison, we can still see that there's a lot of meat left over. So we'll come along and do a profile finishing here. And what this will do is just do a smooth operation on the surface. Oh, I have accidentally allowed it to do some grooving. I'm going to change that behavior by editing the passes tab and unselecting grooving. Lovely, great. So we can see now simulate. Hit play. And then a smooth profile in the end. So just 3 more things are needed. We need some grooving operations here. We need some drilling here. And then we need to part this at the back. So we'll go ahead and do those things now. We'll come along and do the drill first. We'll choose drill and it automatically chose the 4 millimeter drill. All we need to do is pick the hole that we wish to drill. And as before, under the heights tab, click drill tip through bottom. For the cycling, we'll do as before, chip breaking, where we'll allow it to go in pecking depth of 1 millimeter. And we want it to dwell at the end for 0.2 millimeters. Lovely. Next is the grooving. So here we can choose the grooving tool. And by default, if we were to just click OK, what you'd find is it would want to groove the whole thing. That's because it doesn't know what's a pocket, a groovable pocket and what's not. So we'll go ahead and we'll give it some region. We'll say selection. That's the front. And for the back, here. So we just say we would just want Inventor to groove between these areas. And come along to the passes tab. And here we can see that we've got some roughing passes. That's okay. For the radii, here's where is it starting the grooving operation. Because we already removed a lot of material to this point, what we can do is choose the outer radius to be this selection here, plus maybe about 0.2. Great. All right. And we will have a look at what those look like so far. So simulate. And we'll hit. Turn off the stock. Here we can see the drilling operation with its pecking. And then here we've got the grooving operation. Lovely. the final bit with this is the parting operation. So we have to actually cut this back bit off. So to do that, we'll come along here and click, where is it? Part. There we go, in which case it will automatically execute a parting operation at the back. So if we run the whole simulation, oops, we'll turn on the stock. And here we can see, oops, don't run the simulations with part comparison turn on, it turns very slow. There we go, we got facing operation, roughing operation. Smooth finish, drilling, then coming here and grooving, and then doing a final parting operation. Done. So in each of these machining operations, once you've got the toolpaths, if you've got a post-process, if you're happy with your things, then you can see two things in the corner here. We've got post-process, which will turn it into the NC code for your machine, and setup sheet. So this is a setup sheet that it gets spat out. And what it does is it provides us with a list of all of the tools and all of the operations used in the cut, along with speeds and feeds and all of that good stuff, time estimates. There is one last thing that I'd like to show you before we run out of time. So we're overrunning a little bit here. And that's the turning 4+1 operation. So if you have a 4-axis turning machine, it's possible to cut out pockets onto the sides of something. I might actually simplify this a little bit. Actually, we'll just generate the toolpath. If you have a 4-axis machine, it's possible to have that a machining tool come in from the side and drill. When you click the simulate, it will look like the tool is flying around the part, when in reality, the tool is staying still and it's the part that's rotating. Lovely. Okay, I'm sorry, we've overrun a little bit. Thank you very much for your time today. So I gave this presentation on behalf of Crosstech, and here we provide training consultancy for everything Inventor and Fusion 360. So if you have any need for those things, please don't hesitate to get in touch. Otherwise, have a great day. Thank you very much. Cheers. Bye.
Thanks, guys, for watching. If you have any further questions, please don't hesitate to get in touch at info@crosstechgroup.com.au, or you can visit our website at www.crosstechgroup.com.au. And we will be running some Inventor CAM training coming up soon. If you would like some more information on that, please do let us know. Thanks. Bye.